Okay, everyone, let's look at this scenario to start off today. Before spring began, a large tree had only 4 leaves on its branches. Then, when spring began, the number of leaves this tree had tripled every week. Find a formula for a function f of x for the number of leaves on the tree after x weeks. Okay, we want to find a formula for a function, right? Where the value of the function f of x is the number of trees after x weeks, okay? All right, let's see what we can do here. We know before spring even started, we know that before spring even started, it had 4 leaves on its branches, right? So for f of 0 is going to equal 4. Because this is before spring even starts, right? F of 0 weeks since spring has started, okay? All right, so then when spring began, the number of leaves of the tree tripled every week, right? So F of 1 week later, it had 4 times 3, 12 leaves, right? Okay, let's keep going with this and see if we can end up figuring out a good formula. F of 2. Okay, if it's going to triple every week, this is geometric. That means we're going to take our last term and multiply it by 3. In this case, we're going to get 36, okay? To find f of 3, right, we're going to take our last term again. There were 36 leaves after the second week, so after the third week, there were 36 times 3 leaves. And what's 36 times 3? It's 108, right? Okay, and so on. All right, let's see if we can use this pattern to find a good formula for our function. All right, let's remember that, and let's take a minute and think about something over here, right? Well, at f of 0, right, we had 4, right? At f of 1, we took our initial value and multiplied it by 3, right? F of 2, we took our value for f of 1 and multiplied by 3 again. Well, that's like taking 4 times 3, right? Multiplying by 3 again, right? At f of 3, we took our value for f of 2 and multiplied by 3 again, right? Well, that's like taking 4 times 3 times 3, multiplying by 3 again, and so on. And obviously, we know f of 4, right? F of 4 would be the same thing, right? We would take our last term, 4 times 3 times 3 times 3, right? And multiply by 3 again. Okay, so can we simplify this at all? Well, let's look at f of 1 first, actually. F of 1, 4 times 3, well, that's like 4 times 3 to the first power, right? Okay, f of 2, 4 times 3 times 3, well, that's like 4 times 3 to the second power, isn't it? Okay, f of 3 is 4 times 3 times 3 times 3. Well, isn't that like 4 times 3 to the third power? It certainly is, right? That's the same as saying 4 times 3 to the third power. See the value of exponents now? And what about f of 4? That's 4 times 3 times 3 times 3 times 3. 4 times 3 to the fourth power in this case, right? Let me get rid of these markings here. F of 4 is going to be 4 times 3 to the fourth power, okay? And what if we wanted to keep this pattern of 4 times 3 to some power all the way back to f of 0? Well, 4 is just 4 times 1, right? Clearly. And 1 we can write as 3 to the 0th power, right? Because hopefully we remember any number raised to the 0th power is equal to 1. So f of 0 is 4 times 3 to the 0 power. F of 1 is 4 times 3 to the first power. F of 2 is 4 times 3 to the second power. F of 3 is 4 times 3 to the third power, and f of 4 is 4 times 3 to the fourth power, right? So there's a very clear formula going on here, isn't there? Let me erase this to make some room. And what is that formula? Well, it's f of x f of x equals 4 times 3 to the x power, right? That's our formula. F of 0, 4 times 3 to the 0. F of 1, 4 times 3 to the 1. F of 4, 4 times 3 to the 4th power. And of course, we could use this formula to find any value of f, right? What if we wanted to know how many leaves are on the tree after, let's say, 8 weeks, right? How many leaves are on the tree after 8 weeks? Well, that's going to be f of 8, right? F of 8 is going to be 4 times 3. Where's our independent variable here? 4 times 3 to the 8th power, right? Which is going to be 4 times, what is 3 to the 8th power? It's a pretty big number. That's going to be 4 times 6,561, and that's going to be 26,244, right? See, this is a relationship that grows very, very fast, and we can find the value for the number of leaves on the tree after any number of weeks. Now that we have our function, f of x equals 4 times 3 to the x power. Let's take a minute to see if we can generalize this formula we just found, right? Let's see if we can generalize this formula we've just found. Let me create some room here. So we found that f of x in this case is equal to 4 times 3x, right? Well, what was the 4? What was the 4 in this scenario? Wasn't that the initial value? Wasn't that the initial value? And what was the 3? Wasn't the 3 the common ratio, right? Wasn't the 3 the common ratio? It was, right? So for any geometric function, now that we have that information, let me create some more room for this important statement, right? If we have we get some green, if we have a geometric function, right? Function. Let's take the variable a to equal the initial value. Why does this keep happening? A is going to equal the initial value of any geometric relationship. Let's call B our common ratio, okay? Let's call B our common ratio, all right? So we can construct all geometric functions in this form. F of x equals a times b to the x power, okay? Where a is the where a is the initial value, like right here, and b is the common ratio. F of x equals a times b to the x power.